You know what astronomers rely on more than almost anything else? Consistency. The universe changes, sure, but it changes in predictable ways according to known physics. Stars age over billions of years. Planets orbit with clockwork precision. Even comets, chaotic as they seem with their tails and outbursts, follow understandable patterns. As they approach the sun, they heat up. Ice subliments, they get brighter. As they move away, they cool down. Activity decreases, they fade. The relationship between distance, temperature, and brightness is well established. We can predict how bright a comet should be at any given point in its orbit based on its size, composition, and distance from the sun. It's one of the foundational principles of cometary science. So when an object violates those principles, when it gets dramatically brighter or darker, for reasons that don't fit any known physics, astronomers pay attention. And when that brightening happens in a matter of weeks, rather than the months or years that natural processes require, attention turns to alarm. Because at that point, you're not watching a comet behave unexpectedly. You're watching something change in ways that suggest either your understanding of fundamental physics is wrong or the object isn't what you thought it was. 3. I/Atlas went through exactly that kind of transformation between late November to 2025 and early January 2026, and we know about it in extraordinary detail because one of the world's most sophisticated imaging systems happened to be watching at exactly the right time. The Very Large Telescope in Chile is, despite its straightforward name, one of the most powerful ground-based observatories on Earth. It's not a single telescope, but an array of 4 main telescopes and 4 auxiliary telescopes, working together through interferometry to achieve resolution that rivals space-based instruments. Located on Cerro Paranal in the Atacama Desert at an altitude of 2,635 meters, the VLT benefits from some of the clearest, darkest skies available anywhere. And mounted on one of those telescopes is an instrument called SPHERE. SPHERE stands for Spectral Polarimetric High Contrast Exoplanet Research, and as the name suggests, it was designed primarily to directly image exoplanets. That's incredibly difficult. Planets don't emit their own light, they only reflect light from their stars, and they're typically billions of times fainter than those stars. To see a planet next to its star is like trying to see a firefly next to a searchlight from thousands of kilometers away. SPHERE does this through a combination of adaptive optics that correct for atmospheric turbulence, coronagraphs that block the star's light, and sophisticated image processing that teases out the faint signal of reflected light from the planet. But SPHERE isn't just for exoplanets. The same capabilities that let it image faint objects near bright stars make it excellent for studying small bodies in our own solar system. Asteroids, moons, and yes, comets. Particularly comets that are bright enough to be interesting, but small enough that most telescopes can't resolve surface details. When 3I/Atlas made its passage through the inner solar system, SPHERE was one of several instruments assigned to observe it, gathering high-resolution images and spectroscopic data that would help characterize this rare interstellar visitor. Dr. Julien Milly from the Institut de Planétologie et d'Astrophysique de Grenoble leads one of the SPHERE science teams focused on solar system observations. His group had been allocated telescope time to observe 3I/Atlas during its perihelion passage, with observations scheduled in October, November, and December 2025 to track how the comet's appearance changed as it rounded the sun. This wasn't just about 3I/Atlas specifically. Any interstellar comet is a treasure trove of data, a sample of material from another stellar system that you can study without launching an interstellar probe. The more detailed observations, the better. The first SPHERE observations of 3I/Atlas were conducted on October 23, 2025, when the comet was about 1.8 astronomical units from the sun, still approaching perihelion. The images were spectacular. SPHERE resolved the nucleus, a dark, irregular shape about 2.1 kilometers across at its longest axis, surrounded by a diffuse coma of gas and dust. The team measured the nucleus's brightness, which in astronomy we quantify as albedo, the fraction of incident light that a surface reflects. Most comets have very low albedos, typically between 0.03 and 0.06, because they're covered in dark organic compounds and dust. 3I/Atlas fit right in that range. The initial measurements gave an albedo of 0.041, plus or minus 0.003, dark, about as dark as charcoal, roughly the same reflectivity as other cometary nuclei we've studied up close. That number tells you something about composition. A surface with an albedo of 0.04 is absorbing 96% of the sunlight that hits it, reflecting only 4%. That's consistent with a mixture of water ice, rocky material, and complex organic molecules that have been processed by radiation and heat into dark, carbon-rich compounds called tholins. It's what we expect from objects that formed in the outer solar system or, in this case, around other stars in cold molecular clouds. The low albedo also matched the spectroscopic data showing strong organic molecule signatures in 3I/Atlas's outgassing. Everything fit together into a coherent picture of a typical, if interstellar, cometary body. The second set of sphere observations happened on November the 29th, 2025, about 5 weeks after the first. By this point, 3I/Atlas had passed perihelion on October the 29th and was starting its outbound journey. It was now about 1.4 astronomical units from the Sun, a bit closer to Earth than the first observations, but moving away from the Sun and theoretically starting to cool down. The team expected to see the comet a bit less active, maybe slightly fainter overall as sublimation rates decreased. What they didn't expect was for the nucleus itself to look different. But it did. The November images showed a nucleus that was noticeably brighter than before. Not brighter because it was more active, not brighter because of increased outgassing or a better viewing angle. The nucleus itself, the solid body at the center of the coma, was reflecting more light. Dr. Millie's team ran the photometry analysis, carefully measuring the brightness of the nucleus, separate from the surrounding gas and dust. The albedo had increased to 0.089 plus or minus 0.005, more than double what it had been 5 weeks earlier. That was unusual, but not immediately alarming. Comets can undergo surface changes. As ice sublimates away, it can expose fresh material underneath that might be brighter. Dust can get blown off by outgassing, revealing cleaner ice. The team noted the change, made sure it wasn't an artifact of different observation conditions or data processing, and scheduled additional observations to see if the trend continued. The third observation session was on January 4th, 2026, 6 weeks after the second. 3I/Atlas was now about 1.9 astronomical units from the Sun, significantly farther out than the November observations, definitely in the cooling down phase of its orbit. Activity should have been decreasing, the nucleus should have been getting darker as fresh sublimation slowed and dust settled back onto the surface. Instead, it was brighter, much brighter. The January albedo measurement came in at 0.173, plus or minus 0.007. That's an increase of 340% from the October value. The nucleus had gone from darker than charcoal to roughly the reflectivity of concrete or lunar regolith. And this happened over a span of just 10 weeks during a period when the comet was moving away from the Sun and should have been becoming less active, not more reflective. Dr. Millie's first reaction was to assume something had gone wrong with the data. Measurement errors, calibration problems, contamination from bright dust in the coma, making the nucleus look brighter than it actually was. But Sphere's data reduction pipeline includes extensive quality control specifically to avoid these kinds of errors. The images were clean. The photometry was solid. Multiple independent analyses by different team members all came back with the same result. The albedo increase was real. The team immediately contacted other observatories that had been tracking 3I/Atlas, asking if they'd seen similar changes. The Hubble Space Telescope had observed the comet in late December, right between the November and January sphere observations. When the HST team reanalyzed their data, specifically looking at nucleus brightness, they found the same trend. The nucleus was brighter in December than it had been in their October observations. Not quite as dramatic as the sphere measurements, the resolution wasn't as good, but consistent with a progressive brightening over time. Ground-based observatories in Hawaii, California, and Spain all reported similar findings when they went back through their photometry. Everyone had been focused on the comet's overall brightness and activity, tracking the coma and tail, analyzing spectra. The nucleus itself, just a few pixels even in the best images from most telescopes, hadn't been receiving individual attention. But when you isolated it, when you measured just that central point of light carefully, the brightening was undeniable. Between late October and early January, 3I/Atlas's surface had become more than 3 times more reflective. Now, a 340% change in albedo might not sound like much to someone unfamiliar with planetary science. Surfaces change, right? Things get lighter or darker. What's the big deal? But in the context of cometary physics, this is profound. Let me explain why. Comet surfaces are shaped by sublimation, the process where ice turns directly from solid to gas when heated by the sun. As a comet approaches the sun, surface ice sublimates, carrying away dust particles and creating the familiar coma and tail. This process generally makes surfaces darker over time, not brighter. Here's why. Fresh cometary ice, when it's first exposed, might be relatively bright, with an albedo of 0.5 or even higher if it's clean water ice. But as the ice sublimates, it leaves behind non-volatile materials, the dust and organic compounds that don't vaporize. These materials accumulate on the surface, forming a dark lag deposit. Over multiple passages near the sun, comets develop thick crusts of this dark material, which is why most cometary nuclei we've studied are so dark. The only way to make a comet surface brighter through natural processes is to expose fresh ice from underneath, either by having the lag deposit blow off due to outgassing pressure, or by having the surface crack and reveal pristine material below. But those processes happen during active sublimation, when the comet is near the sun and heating up. They don't happen when the comet is moving away from the sun and cooling down. And even when they do happen, they produce localized bright patches, not a uniform brightening of the entire surface. The sphere images showed the whole nucleus getting brighter, not just specific regions. There's another problem. The brightening continued even as the comet's activity decreased. You could see it in the observational data. The coma was getting less dense, the dust production rate was dropping, all the signs that sublimation was slowing down as 3I/Atlas moved farther from the sun. But somehow, simultaneously, the surface was becoming more reflective. That's backwards. If sublimation were exposing fresh ice, you'd expect to see increased activity at the same time, more gas production, more dust. Instead, activity was decreasing while reflectivity increased. Dr. Sarah Hirsch from Johns Hopkins University, who specializes in planetary surface chemistry, was brought in to consult on possible explanations. She pointed out that there are phase changes that can affect albedo without requiring active sublimation. Amorphous ice can crystallize when warmed, and crystalline ice is more reflective than amorphous ice, but that process also happens when approaching the sun, not when moving away. And it produces a much smaller change in reflectivity, maybe 20 or 30%, not 340%. Another possibility is that the surface composition was changing, not through sublimation, but through some kind of chemical reaction or phase transition. Organic compounds on the surface could be degrading under solar ultraviolet radiation, breaking down into simpler molecules that might be lighter in color. But those photochemical processes also slow down with distance from the sun, and they typically darken surfaces rather than brighten them, creating more complex carbon-rich molecules like tholins. By mid-January, Dr. Millie's team had exhausted the conventional explanations. Every process they could think of either went in the wrong direction, produced too small an effect, or required conditions that didn't match the observations. They were left with measurements showing an impossible change. A comet's surface transforming from dark to bright while moving away from the sun, doing so uniformly across the entire visible nucleus, completing the transformation in just 6 weeks. None of the physics made sense. So when standard explanations fail, you go deeper into the data. You look at everything the instruments can tell you, not just the simple brightness measurements, but the fine details of how light interacts with the surface. Sphere isn't just a camera, it's a polarimeter, which means it can measure the polarization state of reflected light. That might sound esoteric, but polarization data reveals information about surface texture and composition that simple photometry can't provide. Smooth surfaces polarize light differently than rough surfaces. Icy surfaces create different polarization patterns than rocky or dusty surfaces. By analyzing how 3I/Atlas polarized the sunlight, reflecting off its nucleus, the team could potentially figure out what kind of surface change was producing the brightening. Dr. Millie pulled the polarimetry data from all 3 observation epochs and started comparing them. The October data showed a polarization signature consistent with what you'd expect from a rough, dusty surface covered in dark organic material. Low reflectivity, high polarization fraction, the light scattering in ways that indicated an irregular surface texture at scales of micrometers to millimeters. Think of it like looking at a surface covered in soot or graphite powder. Lots of tiny particles. Lots of surface irregularity, light bouncing around in random directions before escaping. The November data was different. The polarization fraction had decreased, and the pattern had shifted. Less scattering, more specular reflection, characteristics that suggested a smoother surface or a change in surface composition toward materials with different optical properties. It was still consistent with a natural surface, nothing obviously artificial, but the change was significant. In 5 weeks, the surface texture had evolved from rough and particulate to something more consolidated. The January data was even more striking. The polarization signature looked almost nothing like October. The nucleus was reflecting light with a polarization pattern, more typical of a crystalline or glassy surface. Very low polarization fraction, which happens when light bounces off smooth, ordered structures rather than disordered particle aggregates. The closest analog in solar system bodies would be something like the icy surfaces of some of Saturn's moons, after they've been processed by radiation into a more crystalline state. But those surfaces take thousands or millions of years to develop that character through slow bombardment by energetic particles. 3I/Atlas had done it in 10 weeks. Dr. Anthony Colaprete from NASA, Ames Research Center, who works on the optical properties of ices and has done laboratory simulations of cometary surfaces, reviewed the sphere polarimetry data at the team's request. His first comment was that the progression looked nothing like any cometary evolution he'd seen in laboratory experiments or spacecraft observations. When you heat cometary ice analogs in the lab, when you simulate sublimation under various conditions, you can produce brightening through exposure of fresh ice, but the polarization signature stays rough. The surface might get brighter as darker material sublimates away, but it remains texturally irregular because sublimation is inherently an irregular process. Some areas sublimate faster than others, creating pits and ridges and uneven terrain. What the sphere data showed was the opposite. The surface was becoming uniformly smoother while simultaneously becoming more reflective. That combination suggested not a subtractive process, like sublimation removing material, but an additive or transformative process. Something was either coating the surface with a new material, or the existing surface material was undergoing a phase transition that made it both brighter and smoother. But what physical process could do that to an entire cometary nucleus uniformly over just a few weeks? The spectroscopic data added another layer of mystery. Sphere's integral field spectrograph can take spectra across the entire field of view, creating a three-dimensional data cube where each pixel has a full spectrum. By comparing spectra from the nucleus at different observation epochs, the team could track changes in surface composition, and there were changes. Significant ones. The October spectrum showed strong absorption features, characteristic of organic compounds. Broad absorption across the visible and near-infrared, consistent with complex carbon-rich molecules like tholins and polycyclic aromatic hydrocarbons. This is standard comet stuff, the kind of spectrum you expect from any dark cometary surface. There were also weak absorption features attributable to water ice and maybe some silicate minerals, but the organics dominated. The November spectrum showed the organic absorption features weakening, not disappearing, but becoming less pronounced. At the same time, there were new features emerging in the near-infrared, absorption bands that look like crystalline water ice, and not just any water ice, but a specific crystalline structure. Dr. Emily Skloot from the Planetary Science Institute recognized the spectral signatures immediately. They matched laboratory spectra of cubic ice, also called ice IC, a crystalline form that's metastable at normal conditions but can form under specific temperature and pressure regimes. By January, the spectrum had transformed further. The organic features were barely visible, swamped by strong water ice absorptions. But these weren't the broad, messy absorption bands you see in regular polycrystalline ice. These were sharp, well-defined features indicating a high degree of crystalline order, and there were additional features that didn't match any ice phase that forms naturally on comets. Absorption bands in positions consistent with ice layers contaminated or mixed with other compounds, possibly salts or clathrates, structures where water ice forms cages around other molecules. Dr. Skloot ran the January spectrum through every spectral database she had access to, comparing it to laboratory measurements of various ice compositions and structures. The closest match was to artificially annealed ice that had been carefully heated and cooled under controlled conditions to promote crystal growth and purify the structure. Not something you expect to find growing on a comet that's moving away from the sun and cooling down naturally. Here's where the team started having very uncomfortable conversations about whether they were actually looking at a natural process at all, because the combination of observations, the uniform brightening, the progressive smoothing of surface texture, the evolution of spectral features toward more ordered crystalline states, all of it pointed toward something actively processing the surface, not passively responding to solar heating and cooling, but actively transforming. Dr. Milley reached out to colleagues who work on spacecraft materials, people who study how surfaces behave in space environments. They look at things like satellite coatings, how solar panels degrade under radiation exposure, how thermal cycling affects different materials. He asked them, if you wanted to make a dark, rough surface become bright and smooth over a period of weeks, how would you do it? The answers varied, but several themes emerged. You'd need to either deposit a new material on top of the existing surface, or cause the existing material to undergo a phase change. Deposition could happen through outgassing if there was a volatile component in the interior that was sublimating and redepositing on the cold surface as it migrated outward. But that process would create patchy deposits, bright areas where fresh material accumulated, not uniform brightening, and it wouldn't explain the spectral evolution toward crystalline structures. A phase change could work if there was enough energy to drive recrystallization of surface materials. But where would that energy come from? 3. I/Atlas was moving away from the sun. Solar heating was decreasing, radioactive decay in the interior could provide some heat, but not nearly enough to warm the surface to temperatures where ice would recrystallize over such short timescales. You'd need active heating, something generating energy from within the nucleus. Or, one of the spacecraft materials experts suggested, you'd need a smart coating, a surface layer designed to change its properties in response to environmental conditions. Some spacecraft components use coatings that adjust their thermal emissivity or reflectivity based on temperature, protecting sensitive equipment from extreme heat or cold. If something like that existed on a much larger scale, covering an entire object rather than just a spacecraft component, it could explain what they were seeing. But that's not a natural material, that's engineering. Nobody wanted to say it directly, but the implication was clear in all these technical discussions. The surface transformation of 3I/Atlas looked less like geology and more like technology, or at the very least, it looked like a process that natural cometary physics couldn't explain. The team was careful in how they framed this in their preliminary reports. They didn't use words like artificial or designed. They stuck to observational language, anomalous surface evolution, brightening inconsistent with known cometary processes, spectral signatures suggesting active surface processing. But internally, in emails and video calls where they could speak more freely, the scientists were grappling with possibilities that sounded more like science fiction than science. What if 3I/Atlas wasn't just a comet? What if it was, or had been, something else? And what they were watching was some kind of system activation. The brightening surface, the crystalline transformation, could those be signs of dormant systems coming online as the object moved through the solar system? Dr. Milley didn't want to jump to conclusions like that. He's a scientist, trained to follow the data wherever it leads, but also trained to exhaust mundane explanations before entertaining extraordinary ones. So he pushed for more observations, more data, anything that could either confirm the strangeness or reveal a conventional explanation they'd missed. Additional observations were scheduled, not just with Sphere, but with every available facility that could contribute. The Keck Observatory in Hawaii was tasked with taking high-resolution infrared spectra to look for thermal emission signatures that might indicate internal heat sources. The Gemini North Telescope would use adaptive optics imaging in multiple filters to map surface brightness variations and look for any spatial patterns in the brightening. The Atacama Large Millimeter Array would observe at longer wavelengths to probe subsurface temperatures and composition. And there was one more comparison that needed to be made. We have visited comets before. The Rosetta mission spent 2 years with Comet 67P/Churyumov-Gerasimenko, mapping its surface in extraordinary detail, watching how it changed as it approached and receded from the sun. The Deep Impact mission smashed a probe into Comet Tempel 1 and analyzed the debris. Stardust collected samples from Comet Wild 2 and returned them to Earth. We have high-resolution data on how real cometary surfaces behave, what they look like up close, how they change over time. Dr. Milley's team pulled every piece of comparative data they could find. Rosetta's OSIRIS cameras had tracked surface changes on 67P over its entire perihelion passage. Did anything similar to what they were seeing on 3I/Atlas happen there? No. 67P's surface changed, yes. Some areas brightened temporarily as fresh ice was exposed. Some areas darkened as dust accumulated, but the overall albedo of the nucleus stayed relatively constant, varying by maybe 10 or 15% at most, and the changes were localized and patchy, not uniform. Nothing remotely like a 340% global brightening. The deep impact observations of Tempel 1 showed a very dark surface with an albedo around 0.04, similar to 3I/Atlas's October value. When the impactor hit and excavated subsurface material, the ejecta was brighter than the surface, confirming that there was cleaner ice beneath the dark lag deposit. But even that fresh material had an albedo of only about 0.10 to 0.15, and it darkened again within hours as dust settled back. The brightening was temporary and localized to the impact site. The Stardust samples from Wild 2 contained extremely dark organic material with albedos below 0.05. Laboratory analysis showed these organics were resistant to alteration, maintaining their dark color even when heated or exposed to various chemical treatments. They didn't spontaneously transform into bright crystalline material. Every comparison pointed to the same conclusion. What was happening to 3I/Atlas's surface was not typical cometary behavior. It was not within the range of variation observed in any other comet we'd studied. The brightening was too large, too uniform, too rapid, and it was happening under conditions, moving away from the sun in a cooling environment where it shouldn't be happening at all. The follow-up observations started rolling in through late January and early February, and each new dataset added detail to the picture while deepening the mystery. The Keck Observatory's NIRSPEC instrument obtained high-resolution infrared spectra on January 18th, focusing specifically on thermal emission from the nucleus. What they found was unexpected enough that the observing team ran the data reduction twice to make sure they hadn't made an error. 3. I/Atlas was radiating more heat than it should have been. When an object in space absorbs sunlight, it heats up until it reaches an equilibrium temperature where the energy it radiates as thermal infrared balances the energy it absorbs. For a dark object at 1.9 astronomical units from the sun, that equilibrium temperature should be around 180 Kelvin, maybe 190 if the surface is particularly good at absorbing solar radiation. The Keck data showed the nucleus at 217 Kelvin. That's almost 30 degrees warmer than solar heating alone could explain. Dr. Yanga Fernandez from the University of Central Florida, who specializes in thermal modeling of small bodies, analyzed the Keck data and tried to account for the discrepancy. Could the brightening surface be affecting the thermal balance, making the object absorb less sunlight and therefore radiate at a different temperature? No, that would make it cooler, not warmer. A brighter surface reflects more light, absorbs less, and should equilibrate at a lower temperature. Could there be some unusual thermal properties? Maybe the surface has low thermal inertia that causes temperature variations that could create localized hotspots but wouldn't raise the average temperature across the entire nucleus. The only explanation that fit was an internal heat source. Something inside 3I/Atlas was generating energy, warming the nucleus from within. That heat was conducting through the interior and radiating from the surface, adding to the solar heating and pushing the temperature higher than equilibrium. Fernandez calculated that the internal heat generation would need to be on the order of several hundred watts per square meter of surface area to produce the observed temperature excess. For the entire nucleus, that totaled to roughly 50 megawatts of power output. Where could that power come from? Radioactive decay is the usual internal heat source for planetary bodies, but the power output from realistic amounts of radioactive elements in a comet-sized object would be orders of magnitude too small. You'd need concentrations of radioactive isotopes far higher than anything seen in meteorites or solar system materials. Chemical reactions, maybe exothermic decomposition of unstable compounds? Possible in principle, but again, the power levels don't match. You'd need the entire nucleus to be made of high-energy materials undergoing rapid decomposition, and that would show up in other ways, like massive outgassing or structural changes. Tidal heating was another possibility the team considered. When an object passes close to a massive body like a planet, gravitational tidal forces can flex the interior, generating heat through friction. Jupiter's moon Io is the classic example, kept molten by tidal heating from Jupiter's gravity. But 3. I/Atlas hadn't passed close to any planet on this orbit. It had come within reasonable proximity to Earth, about 270 million kilometers at closest approach, but that's nowhere near close enough to generate significant tidal heating. And besides, tidal heating is strongest during close approach and fades afterward. The temperature excess was being measured more than a month after Earth's closest approach, when any tidal heating should have dissipated. That left few options. Either there was an energy source in the nucleus that we don't understand, some exotic process not accounted for in standard models, or the object was using stored energy, releasing heat that had been accumulated somehow during its journey through space. Neither explanation was particularly comforting. Both implied that 3I/Atlas was not behaving like a typical comet. The Gemini North observations, conducted January 21st to 22nd, provided spatial resolution of the brightening. Using adaptive optics in 5 different filters ranging from visible to near infrared, the telescope mapped brightness variations across the nucleus, and there were variations. The surface wasn't uniformly bright. There were patches of higher and lower reflectivity, patterns that suggested structure beneath the surface or differential evolution of surface properties. Dr. Amanda Sikafus from the Planetary Science Institute in South Africa analyzed the Gemini images looking for patterns. What she found was geometric. The bright patches weren't randomly distributed. They formed lines, intersections, boundaries that looked almost architectural. Imagine looking at an aerial photograph of a city and seeing the street grid. Not that 3I/Atlas looked like a city, but the distribution of bright and dark areas had a regularity that natural processes don't typically produce. She measured the angles between some of the linear features. Several of them were oriented at 60 or 120 degrees to each other, forming triangular or hexagonal patterns. Others were perpendicular, creating rectangular grids. The patterns were subtle, you wouldn't notice them in low-resolution images, but at Gemini's resolution, they were clear, and they were evolving. Comparison with earlier Hubble images showed that the patterns had become more defined over time, as if whatever process was brightening the surface was following or revealing underlying structures. This geometric organization was troubling for the same reason the uniform brightening was troubling. Natural surfaces, shaped by impacts, sublimation, and thermal stress, create irregular features. Cracks follow stress patterns that depend on material properties and temperature gradients, producing fracture networks that look organic, branching, chaotic. What the Gemini images showed looked organized, planned, as if the surface was a shell covering something structured beneath. Dr. Sisyphus didn't want to overinterpret the data. Maybe there were natural explanations. Maybe the nucleus had an unusual internal structure, layers of different materials with different sublimation rates, and what looked like geometric patterns were just the outlines of those layers being revealed as surface material eroded away. Maybe. But when she showed the images to colleagues who work on spacecraft thermal design, their immediate reaction was that it looked like a thermal blanket or insulation pattern, the kind of thing you see on satellites where different materials are arranged to control heat flow in specific ways. The ALMA observations from late January were perhaps the most puzzling of all. ALMA observes at millimeter wavelengths, which penetrate beneath surfaces and can reveal temperature and composition several meters deep. The data showed something strange. The subsurface temperatures were higher than the surface temperatures. Normally it's the opposite. The sun heats the surface, and that heat slowly conducts inward, creating a temperature gradient where the surface is warmest and the deep interior is coldest. What ALMA saw on 3I/Atlas was inverted. The surface was at 217 Kelvin based on the Keck measurements, but a few meters down, the temperature was estimated at 240 Kelvin or higher. Dr. Martin Cordner from NASA Goddard, who led the ALMA observation analysis, ran thermal models trying to reproduce that inverted gradient. You could do it if there was an internal heat source distributed through the interior, but then why wasn't the surface even hotter? The heat should conduct outward and elevate surface temperatures too. Unless something was preventing the heat from reaching the surface efficiently, some kind of thermal insulation layer right below the surface that allowed heat to build up underneath while keeping the surface relatively cool. But wait, that doesn't make sense either. If the subsurface was hot and the surface was cool, heat would flow upward through conduction and you'd equilibrate. You can't maintain a steep inverted temperature gradient unless you're actively removing heat from the surface or actively adding heat below the surface, or both. That requires energy expenditure, active thermal management. That's not something a comet does. That's something an engineered system does. Cordner's team also detected anomalous emission lines in the ALMA data, molecular signatures that didn't match the expected composition. Carbon monoxide was there, as expected from earlier observations. Water vapor, sure. But there were lines that look like silicate minerals at temperatures where they should be solid, not producing emission. And there were unidentified features, emission at frequencies that didn't correspond to any common molecule in the spectral databases. When you combine all these observations, the Keck thermal excess, the Gemini geometric patterns, the ALMA inverted temperature gradient and unusual chemistry, the sphere brightening and crystalline spectra, you're left with a picture of an object that's doing things comets don't do. Objects in space are passive. They absorb energy from the sun, they radiate it away, they respond to thermal stress, they sublimate, they crack, they erode, they don't actively heat themselves from within at power levels inconsistent with any known natural heat source. They don't develop geometric patterns on their surfaces. They don't maintain inverted temperature gradients that require active thermal control, unless they're not passive, unless something inside is active. The team started drafting a paper for publication in late January. The writing process was difficult because they had to present findings that challenged fundamental assumptions without sounding sensationalist or unscientific. Dr. Milley worked with Dr. Polarimetry, Dr. Fernandez, Dr. Sisyphus, Dr. Cordner, and several others to craft a manuscript that laid out the observations clearly, acknowledged the limitations of the data, and discussed possible explanations, both conventional and unconventional. The draft went through multiple revisions. Early versions included more speculative language, discussing the implications if the observations truly indicated active processes. Later revisions pulled back, focusing strictly on the measurements and leaving interpretation more open-ended. The final version, submitted to Nature Astronomy in early February, was titled Anomalous Surface Brightening and Thermal Properties of Interstellar Comet 3 ANS-I/Atlas. The abstract noted the 340% albedo increase, the thermal emission excess, the geometric surface patterns, and the inverted subsurface temperature gradient, concluding that these observations are inconsistent with standard cometary evolution models and may indicate internal processes not previously observed in cometary bodies. The paper was immediately flagged for expedited review given the significance of the findings. Within days, it was in the hands of referees. Experts in cometary physics and planetary science asked to evaluate whether the observations were sound and the conclusions justified. The reviews came back in 3 weeks, faster than usual. 2 of the 3 reviewers recommended publication with minor revisions. The third reviewer was more critical, arguing that the team hadn't adequately ruled out all conventional explanations and that the language, even as cautious as it was, came too close to implying something extraordinary. That third review included a comment that captured the tension underlying the whole discussion. The observations presented are of high quality and clearly show unusual behavior. However, the authors must be careful not to let the intrinsic strangeness of the data lead them toward interpretations that, while technically possible, are not the most parsimonious. Before suggesting internal activity or processes requiring energy expenditure beyond known sources, we should exhaust every conceivable natural mechanism, no matter how unlikely it might seem. The standards of evidence for extraordinary claims remain high, and rightfully so. Dr. Milley and his co-authors took that feedback seriously. They added a section to the paper, systematically going through every conventional explanation they could think of and showing with calculations and references to previous work why each one failed to account for the observations. Unusual sublimation geometry doesn't explain the thermal excess or inverted gradient. Surface ice phase transitions can't happen uniformly across the entire nucleus over just weeks. Tidal heating, no close planetary encounter, radioactive decay, insufficient power output by orders of magnitude, exothermic chemistry would produce vastly more outgassing than observed. The revised paper was accepted for publication on February 19, 2026 and appeared online 3 days later. The response from the scientific community was immediate and divided. Some researchers praised the careful observational work and agreed that the findings were genuinely anomalous, deserving of serious attention and follow-up study. Others were more skeptical, arguing that while the data was interesting, the interpretations were premature, that there must be mundane explanations that hadn't been considered yet. And a few, though they wouldn't say so publicly, were quietly alarmed, because they'd been seeing similar strangeness in their own data on 3I/Atlas and hadn't known quite what to make of it. Dr. Karen Meach from the University of Hawaii, one of the world's leading experts on comets and a key figure in the study of interstellar objects, gave a measured response in an interview with Nature News. She acknowledged that the albedo change was unprecedented in magnitude and rate, that the thermal observations were puzzling, and that the geometric patterns warranted investigation, but she also cautioned against jumping to exotic explanations. We're dealing with an object from another stellar system, potentially formed under very different conditions than solar system comets. It's possible that interstellar comets have properties and behaviors we simply haven't encountered before. That doesn't mean they're artificial or actively powered. It means our models are incomplete. That position represented the mainstream view among planetary scientists, at least publicly. Unknown natural processes, exotic materials, formation conditions we don't fully understand. Keep looking for conventional explanations. Don't invoke extraordinary mechanisms until absolutely necessary. It's the right scientific approach, the careful conservative methodology that prevents us from seeing patterns where none exist or mistaking unusual natural phenomena for something more. But privately, in emails and conference calls, some of the researchers involved were less certain. Dr. Milley received messages from colleagues pointing out that the brightening wasn't the only anomaly. Other teams studying 3I/Atlas had found their own oddities. Unusual rotation behavior that didn't fit a simple tumbling pattern. Radio emissions at specific frequencies that shouldn't be there. Trajectory microcorrections that looked like course adjustments rather than outgassing effects. Each observation by itself could potentially be explained away, attributed to measurement uncertainty or misinterpreted data, but taken together, they painted a picture of an object that was doing a lot of things that natural comets don't do. And then there was the context, the Euclid discovery of 47 objects with identical spectral signatures to 3I/Atlas, some of them on trajectories toward Earth, the Dead Sea Scrolls fragment describing a wandering star that returned, with timing and position information that match 3I/Atlas's calculated previous passage 2,000 years ago. The Greenland ice core evidence showing 3I/Atlas-like chemical markers at the younger, driest boundary, 12,800 years ago, coinciding with a catastrophic climate event and megafaunal extinctions. Each of these findings was based on solid data, published in peer-reviewed journals, but each also pushed against conventional understanding in uncomfortable ways. When you looked at all of it together, when you connected the dots across these separate lines of evidence, a narrative emerged. Not a confirmed narrative, not something anyone could prove definitively, but a possibility that couldn't be ignored. What if 3I/Atlas wasn't a comet in the traditional sense? What if it was something that looked like a comet from a distance, behaved like a comet in some ways, but was actually something else? And what if the brightening surface, the internal heat, the geometric patterns were signs of systems activating, preparations for something yet to come? Dr. Milley didn't particularly want to think along those lines. He's a planetary scientist, not a science fiction author. His career has been built on careful analysis of observational data, on building models that explain how natural objects behave according to known physics. Suggesting that 3I/Atlas might be something other than a natural object would be professional suicide if he was wrong. Even if he was right, it would be career-defining in ways that might not be comfortable. But he also couldn't ignore what the data was showing. The brightening had continued through February. A fourth sphere observation on February 16th showed the albedo now at 0.194, approaching 0.2, nearly 5 times brighter than when observations began in October. The rate of change wasn't slowing down. If anything, it was accelerating. Whatever process was transforming the surface was still active, still progressing. And based on the Keck thermal data showing increasing internal temperatures, the energy source powering the transformation was still running, possibly even ramping up. The team had requested additional telescopes time, trying to track the evolution as closely as possible. The James Webb Space Telescope was scheduled to observe 3I/Atlas again in late February with its mid-infrared instrument, which could provide even more detailed thermal mapping and spectroscopy than previous observations. The Hubble Space Telescope had allocated time for high-resolution imaging in early March. Ground-based observatories were continuing regular monitoring. Everyone wanted to see what would happen next, whether the brightening would plateau, whether it would reverse, or whether it would continue until the entire surface was transformed into something unrecognizable. And there was the question of what happens when the transformation is complete. Assuming it does complete, assuming there's some endpoint to this process, what then? Does the object remain bright and crystalline and hot? Does it do something else? Something that will only become apparent once the surface reaches some threshold state? The uncertainty was maddening. We've never seen anything like this before, which means we have no precedent for predicting what comes next. Dr. Fernandez, working with colleagues at NASA's Jet Propulsion Laboratory, had been running trajectory simulations trying to understand the long-term orbital evolution of 3I/Atlas. The object was currently outbound, moving away from the Sun, headed back toward the outer solar system and eventually into interstellar space. At least, that's what its trajectory suggested based on observations from October through January. But if there were active systems on board, capable of generating significant power, capable of transforming the surface, might those systems also be capable of trajectory modification? The non-gravitational acceleration that had been detected, small velocity changes that didn't match expected outgassing patterns, could those be trajectory corrections? Adjustments to the orbital path for reasons we don't understand? If so, where is 3I/Atlas actually going? Is it leaving the solar system as the orbital calculations suggest, or is it maneuvering to stay, to position itself somewhere specific? Those questions sounded paranoid even to the researchers asking them, but paranoia is just pattern recognition applied to sparse data, and when the patterns you're seeing don't fit comfortable explanations, it's hard not to extrapolate into uncomfortable territory. The brightening surface isn't just an interesting anomaly anymore, it's a transformation, an active process, happening in real time on an object that's already shown multiple other anomalous behaviors, and we're watching it happen, measuring it, documenting it, but we don't understand it. We don't know what it means or what it's building toward. Maybe Dr. Meach is right. Maybe this is all just exotic cometary physics, natural processes shaped by formation conditions we don't encounter in our solar system. Interstellar comets from distant stellar environments, carrying ices and organics and minerals that behave in ways we've never seen before. Give it time, gather more data, and conventional explanations will emerge that account for everything without requiring anything extraordinary. Or maybe, and this is the thought that keeps researchers awake at night, maybe we're watching something wake up. Maybe the passage through the inner solar system, the heating from the sun, triggered systems that had been dormant for thousands of years or longer. Maybe the brightening surface is preparation, a shell being activated or revealed, insulation being cleared away, or reflective surfaces being deployed. Maybe the internal heat is energy being generated for purposes we can't yet determine. Maybe the geometric patterns are functional structures, and we're seeing them emerge as surface materials transform or sublimate away. We don't know. That's the honest answer. We have extraordinary observations that don't fit standard models. We have multiple lines of evidence suggesting that 3I/Atlas and objects like it have been visiting Earth's vicinity for thousands of years, sometimes catastrophically. We have an object that's currently undergoing a transformation we can measure, but not explain, and we don't know what any of it means, or what happens next. Science is supposed to be about certainty, about building reliable models that make testable predictions, but sometimes science is about admitting uncertainty, about recognizing when observations have pushed you beyond the boundaries of understanding into territory where all you can do is watch, measure, and wait to see what the universe reveals next. 3. I/Atlas is now 2.2 astronomical units from the sun and continuing outward, a small bright point of light against the stars, reflecting sunlight with an intensity that should not be possible for a comet that's cooling and moving away. Inside that bright shell, processes are running that we don't understand, transforming the object in ways that violate our assumptions about how natural bodies behave. And we're watching, recording, trying to understand, because whatever 3I/Atlas is, whatever it's becoming, it's happening now, in our time, within reach of our instruments and our ability to observe. We might not get another chance to see something like this. The universe rarely provides such clear opportunities to confront the limits of our knowledge, so we observe, we measure, we publish, we debate. We do what scientists do when confronted with the genuinely unknown. We pay attention, we follow the data, and we wait to see what it teaches us, no matter how strange or unsettling those lessons might be.